Imagine looking up at the night sky and realizing that one of those faint, distant dots of light isn't a star, or a planet, or even a comet from our own solar system, but something much stranger, an alien traveler from a completely different star system, racing past us at unimaginable speeds. For most of human history, that idea was pure science fiction, the kind of thing that only existed in books and movies. But in 2017, that changed forever, when astronomers spotted Oumuamua, the very first interstellar object ever detected in our solar system. Its unusual shape, bizarre movement, and mysterious lack of a comet-like tail baffled scientists and sparked endless speculation. Just 2 years later, another interstellar visitor appeared, Comet Borisov, this time much more ordinary, behaving just like a typical comet, but carrying with it the proof that Oumuamua was not a once-in-a-lifetime fluke. And now, in 2025, the story has taken a dramatic new turn. Astronomers have detected yet another interstellar object, and this one isn't just passing by, it's rewriting the rules of what we thought we knew about our cosmic neighborhood, named 3I Atlas. It is faster, larger, and stranger than anything we've ever seen before, and for the first time in history we are ready for it. The discovery happened on July 1st, 2025, when astronomer Larry Denny submitted what at first looked like just another faint detection in the sky. At magnitude 18.8, it was over 2 million times dimmer than the North Star, barely more than a speck against the crowded background of stars. But there was something unusual about it. Instead of drifting lazily like a normal asteroid, this object was moving with urgency, with speed. Preliminary calculations suggested something astonishing. It wasn't bound to our sun's gravity. It was moving so fast that nothing could hold it here. That fact alone placed it in an entirely new category, but as follow-up observations poured in from around the world, the excitement grew. This was no ordinary asteroid, no long-period comet looping in from the far reaches of the Oort cloud. This was a true outsider, a messenger from another star system. What makes 3I Atlas even more extraordinary is the context of its discovery. Unlike Oumuamua, which we noticed only 5 days after it had already flown past Earth, this time astronomers were ahead of the game. Thanks to networks of telescopes constantly scanning the skies, the object was spotted while it was still inbound, giving scientists a once-in-a-generation opportunity to track and study it in real time. Observatories from Arizona to Chile to Spain turned their instruments toward it, confirming its bizarre trajectory and unprecedented speed. Amateurs joined in too, scouring archival images to find earlier detections that pushed its observational record back by weeks. Each new piece of data painted a clearer picture. This object wasn't just interstellar, it was on the most extreme trajectory ever recorded, moving at a velocity that redefined what scientists thought possible. And yet, the real story of 3I Atlas isn't just about numbers or orbits. It's about the sense of awe and urgency it has created across the global astronomical community. Here was an object that had traveled for millions of years across the galaxy, possibly ejected from its home star system by some violent event long before humans even walked the Earth. Now hurtling past our cosmic doorstep, its path, its speed, even its very existence, all raise profound questions about how many of these visitors might be silently passing by, unseen. More importantly, Atlas isn't just a mystery, it's an opportunity to study, in real time, material from another star system, an opportunity to glimpse for the briefest of moments the shared chemistry and history that ties our solar system to the rest of the galaxy. And maybe, just maybe, an opportunity to learn something about our own origins from a rock that has come so far to cross our path. This is not just another discovery. This is the beginning of a new chapter in our story with the stars. It started like a whisper in the data, another faint point gliding across a crowded star field that most nights would be filed and forgotten. But the night of July 1st, 2025 refused to behave like most nights. Larry Denny, working a routine pass through the Atlas survey stream, saw the dot at magnitude 18.8, an ember barely brighter than the noise, yet it moved with the wrong kind of confidence. Survey software expects asteroids to drift at a predictable pace, tied to the sun like kites on long strings. This thing streaked just a bit too decisively, as if the string had snapped long ago. He hit submit, flagged the motion, and within hours the global relay lit up. Catalina checked, Pan-STARRS checked. Smaller scopes in Arizona and the Canaries added their marks. Each new tracklet nudged the math away from comfort and toward a single unavoidable conclusion: the velocity didn't belong to a local. In plain terms, if you toss a ball hard enough on Earth, it leaves for good. This object had tossed itself out of somewhere far older and wasn't interested in being captured by our star. The initial solution put its speed well beyond solar escape, the kind of number that makes experienced observers go silent for a beat and reread the line. But the real twist came from people far from the big domes. A citizen scientist named Sam Dean dug into public image archives and found it there, days earlier, hiding in frames nobody had flagged, the same faint prickle of light inching against a blizzard of background stars. Another amateur, patient and stubborn, pulled even older shots from Zwicky's transient trove, extending the trail back nearly 2 weeks. Each rediscovered point tightened the curve, turning suspicion into geometry you could stake your reputation on. The eccentricity jumped past 1, then past 2, then kept climbing into territory that barely shows up in textbooks, a hyperbolic scream through the inner system with no return ticket. Suddenly a narrative took shape. The object had threaded the worst possible corridor for discovery, skimming the galactic bulge where billions of stars make every pixel crowded and messy, a perfect place for a traveler to blend in and slip by. That it didn't slip by is the story of modern skywatching, industrial-scale surveys feeding oceans of data to anyone curious enough to dive. Professionals booked emergency time on larger apertures for spectra and precise astrometry. Amateurs coordinated on message boards to keep the cadence alive during gaps. The Minor Planet Center, cautious by design, moved quickly once the numbers refused to budge, issuing the designation that placed it in rare company, our third confirmed interstellar visitor. This wasn't Oumuamua's late notice or Borisov's familiar demeanor. From the start, Atlas felt different, faster, hotter in the math, and showing early hints of activity that said comet before the word appeared in any press release. For a moment, you could feel the community do two things at once: celebrate the catch and wince at what it implied. If this one hid in plain sight for weeks because it skimmed the worst background, how many others have threaded similar gauntlets while our algorithms looked for cleaner skies? That question didn't slow anyone down. Requests for time went out to web schedulers, mid-infrared planners sketched out band passes, optical teams queued photometry runs to beat down the rotation signal buried under a growing coma. The tone everywhere was urgency without panic. Not because it was a threat, it wasn't, but because windows like this close fast. An object moving at tens of kilometers per second doesn't pause so we can get our calibrations right. It gives us one shot to follow, measure, and learn before it slips back into the dark. And the hook for what came next was irresistible. If the discovery alone rewrote assumptions about how often the galaxy knocks on our door, what would its chemistry say about where it came from, and what exactly gets traded between star systems when the universe decides to scatter its die? The breakthrough moment came not from a billion-dollar facility, but from the glow of a laptop screen in the quiet of an amateur astronomer's study. Sam Dean, a citizen scientist known for chasing down oddities buried in public telescope archives, had been combing through Atlas images long after the official discovery alert when he stumbled across a breadcrumb trail. At first glance, they were ordinary frames, faint speckles scattered against the noisy backdrop of the galactic bulge. But as he stitched them together, frame after frame, the same dot appeared, sliding with improbable consistency. He realized the object hadn't just appeared on July 1st. It had been there as early as June 25th, hiding in plain sight. The revelation turned a fragile curve of hours into a robust trajectory spanning days, and in astronomy, more time means more certainty. Suddenly, the error bars shrank, and the orbital solution that once wavered between possibilities snapped into clarity. The eccentricity wasn't just above 1, it soared to a staggering value over 10, a number so extreme it nearly mocked comparison. To put it in perspective, Halley's comet, with its elongated path, barely scratches 0.97, looping back every 76 years. Even the most wayward, long-period comets in our own cloud of debris rarely exceed eccentricities of 3. But this object, it was a hyperbolic missile, flung from elsewhere in the galaxy, with a speed and trajectory so extreme it didn't merely pass through our solar system, it carved through it like a skipping stone, barely touching the pond. And Dean wasn't alone. Once his discovery hit the message boards, others followed the scent. Yao Quanji trawled Zwicky transient facility data and found even earlier detections, stretching the record back to June 14th. What had begun as a dot spotted in a single survey grew into a nearly 3-week-long data trail. Suddenly, astronomers had the kind of coverage usually reserved for routine near-Earth asteroids, except this wasn't routine at all. Each new data point tightened the math, leaving no room for comforting alternatives, like long-period comet or disturbed asteroid. The message was unambiguous. This thing was not from here. The numbers screamed interstellar, and they screamed it louder than ever before. What made the discovery even more remarkable was the realization of how easily it might have slipped away. Positioned directly in front of the galactic center, the most visually chaotic region of the night sky, the object had camouflaged itself against a background crammed with billions of stars. Imagine trying to notice a single firefly in front of a floodlit stadium. That was the challenge. Automated surveys, powerful though they are, struggle in those crowded fields where algorithms choke on noise and false positives. That it was found at all was a testament to the obsessive persistence of amateurs who refused to let anomalies pass unexamined. And yet, the object didn't just exist as a curiosity, it carried with it profound implications. If one interstellar wanderer could nearly slip past unnoticed, how many others had already come and gone, lost in the glare of busy sky? This was more than a discovery, it was a warning that our census of the galaxy's visitors is far from complete. Professional observatories immediately mobilized. Emergency proposals flew across the desks of telescope directors. Time was carved out of packed schedules because everyone knew the window was short. Interstellar objects don't loiter, they blaze through, offering a fleeting chance to capture their light, their spectra, their story. As the data poured in, the global community leaned into collaboration. Professionals, amateurs, even curious hobbyists, all bound together by the urgency of the moment. The tale of this object wasn't just written in the physics of its path, it was written in the hands and eyes of the many people who noticed, measured, and refused to let it vanish unremarked. And as the weeks unfolded, a new tension began to build. This was no ordinary interstellar traveler. The speed was higher, the trajectory more extreme, and the signs of activity undeniable. Unlike Oumuamua, with its strange silence, this one whispered secrets the moment sunlight touched it. The world braced for answers, because what the chemistry revealed next promised to be even stranger than the mathematics. When the numbers finally settled into certainty, what stunned astronomers most was the raw speed of the intruder, now officially designated 3I Atlas. hurtling through the solar system at an astonishing 66 kilometers per second relative to the Sun, it left no doubt that this was not just a visitor, but a visitor of a kind never before witnessed. To put such velocity into perspective, consider that Earth itself moves around the Sun at about 30 kilometers per second. The escape velocity from the solar system, the speed needed to break free of the Sun's gravity, is about 42 kilometers per second. This object wasn't merely above that threshold, it was surpassing it by more than half again, a cosmic sprint that rendered any possibility of capture impossible. Even among known comets and asteroids, nothing native to our solar system comes close. The speed alone told a story of violent beginnings, because objects don't just drift into interstellar space at such breakneck velocities. They are flung somewhere, millions or perhaps billions of years ago, in a system far from our own. Something catastrophic must have happened to send Atlas on its endless journey. Astronomers began to speculate. Was it a near pass by a massive star whose gravity slingshotted it outward at unimaginable force? Or was it the chaos of a planetary system in formation where giant worlds jostled for position and tossed lesser bodies aside like toys? Another possibility, even more dramatic, was that it had been ejected during the death throes of a star, a supernova explosion unleashing such energy that nearby objects were hurled into the galaxy as cosmic bullets. Whatever the origin, the numbers were undeniable, and they painted a picture of a past steeped in violence. But the speed did more than hint at an origin story, it also shaped the present. For astronomers, studying something moving this fast posed a logistical nightmare. Time was always the enemy when it came to interstellar objects, but with 3i Atlas, the urgency was magnified. It would streak across the solar system in months, not years, its observable window narrowing rapidly. Already, calculations showed that by October, it would make its closest approach to the Sun at 1.4 astronomical units inside Mars's orbit, but still comfortably far from Earth, and then it would accelerate away, never to return. By December, it would be so distant and faint that only the most powerful instruments would be able to track it, and after that it would vanish back into the darkness between stars. The object's unprecedented velocity also carried symbolic weight. To many, it felt like a message from the wider galaxy, a tangible reminder that the universe is not static or isolated, but dynamic and connected. These wanderers are emissaries, bringing with them fragments of distant planetary system. And while earlier visitors like Oumuamua and Borisov had already hinted at this truth, 3i Atlas underscored it with new intensity. Its speed, its extreme trajectory, and its visible cometary activity combined into a perfect confirmation. Interstellar visitors aren't rare flukes, but regular messengers, and some of them are unlike anything we've ever imagined. The mathematics of its hyperbolic path were equally astonishing. An eccentricity of over 6, a number so far beyond 1 that it seemed almost absurd, made it the most extreme orbit ever recorded. Hyperbolic trajectories are the telltale sign of something unbound, destined to leave forever. But this wasn't just unbound, it was practically untethered, barely brushing the Sun's influence as it carved through. Astronomers described it as the equivalent of a stone skipping across a pond at such speed, it never really touches the surface, just grazes and departs. The implications were profound. If such objects exist in measurable numbers, then the galaxy may be littered with them, passing through solar systems regularly, each carrying chemical fingerprints of their origin. For planetary scientists, it meant that the building blocks of worlds, the ices, the dust, the organics could be compared across systems, allowing us to test whether the recipes for planets and perhaps life itself are universal or unique. For physicists, the sheer speed raised new questions about the mechanics of ejection. Could planetary systems really sling such massive bodies outward at these velocities, Or did this point to rarer, more exotic mechanisms? And for dreamers, it offered a tantalizing thought. What if one day we had the capability to intercept such an object, to sample directly the material of another star system without ever leaving our own? As these discussions unfolded, observatories around the world worked feverishly to secure every possible observation. Spectrographs split its faint light into rainbows of data, telescopes tracked its motion night after night, and computer models churned to reconstruct its path backward across the galaxy. Somewhere buried in its numbers was the story of its birthplace, and though 3I Atlas would be gone in a blink compared to cosmic timescales, the velocity it carried ensured that it left behind more than a streak through the sky. It left behind a challenge to human curiosity, a dare to chase the next visitor harder, faster, and deeper than ever before. It wasn't just a comet or a rock. It was a messenger, and its incredible speed was both the reason we would lose it and the reason we could not ignore it. What truly set 3I Atlas apart from its predecessors was not only its speed and trajectory, but the astonishing eccentricity of its orbit, a number so extreme that it made even seasoned astronomers stop and stare at their screens in disbelief. Orbital eccentricity is the measure of how much a path deviates from being a perfect circle. Earth, for example, traces a nearly round orbit with an eccentricity of just 0.017. Most planets are similarly modest, and even comets, known for their elongated journeys, rarely exceed values near 1. The Great Halley's Comet, which dives deep into the inner solar system every 76 years before retreating into the outer reaches, has an eccentricity just shy of 1. But when eccentricity surpasses 1, the rules of orbital mechanics shift entirely. The path no longer closes into an ellipse, no longer loops back into familiarity. Instead, it becomes a hyperbola, an open-ended curve that allows only a single pass through the solar system before the traveler vanishes forever into interstellar space. For Atlas, the numbers went far beyond the threshold. Calculations pegged its eccentricity at a record-breaking 6.3, making it the most extreme trajectory ever documented. To understand how radical that is, imagine a stone skipping across the surface of a pond. Most comets, even those on hyperbolic paths, are like stones skimming close to the water's surface, touching long enough to leave ripples. Atlas, by contrast, is a stone flung with such violence that it barely brushes the water at all, grazing the sun's gravity field only enough to curve slightly before launching outward with no intention of return. Such a trajectory isn't just unusual, it's a mathematical proclamation that this object was born elsewhere, molded in an alien system, and hurled outward with unimaginable force. The implications of such an eccentric orbit ripple through multiple scientific disciplines. For planetary scientists, it provides direct confirmation that catastrophic events can eject large icy bodies, not only from the distant edges of planetary systems, but with enough energy to cross the interstellar void for millions of years. For astrophysicists, it highlights the violent dynamics of star systems, where gravitational dances between giant planets, or even stellar explosions, act like slingshots, firing smaller objects into galactic exile. And for astronomers studying the distribution of material in the Milky Way, it offers a tantalizing new data point, suggesting that interstellar wanderers are far more varied in their dynamics than we had ever assumed. The extreme eccentricity also shaped the urgency of observation. A path so open meant Atlas would spend only a fleeting time in our neighborhood, its close approach measured in months rather than years. Once it raced past perihelion, the closest point to the sun, its trajectory would carry it outward at speeds even faster than when it arrived, leaving behind only the faintest dust trail as evidence of its visit. Observers worldwide scrambled to make sense of the fleeting opportunity, knowing this was the kind of discovery that might not come again for decades. Yet eccentricity did more than define its future. It also whispered secrets about its past. Such an extreme value could only be explained by a history of violent encounters. Perhaps Atlas had been caught in a chaotic gravitational crossfire between massive gas giants in its birth system, tossed around until one final encounter sent it hurtling into freedom. Or maybe it had passed perilously close to a dying star. Its gravity warped and twisted before finally ejecting the comet with incredible velocity. Another possibility lay in the cataclysm of a stellar explosion, the sheer energy of a supernova unleashing enough force to fling Atlas outward at speeds few objects ever achieved. Whatever the case, the eccentricity number of 6.3 was not just a statistic, it was the signature of trauma, a cosmic scar etched into the mathematics of its journey. The eccentricity also influenced how astronomers approached their analysis. High eccentricity meant high speed, and high speed meant limited time to extract information. Spectrographs, photometric studies, and imaging campaigns had to be coordinated across the globe, often running back-to-back observations as the comet darted across the sky. Every observation was precious, each one a fragment of a larger puzzle that would soon be impossible to piece together once Atlas slipped back into the abyss. Still, within those numbers was a promise. If Atlas could survive such violence and still carry with it ices, dust and organics from its birth system, then interstellar objects may be more common and more resilient than once imagined. Each eccentric orbit recorded adds another chapter to the story of how planetary systems are born, live, and eventually cast off fragments of themselves into the galaxy. And if Atlas, with its extraordinary eccentricity, could make the journey across untold light years to our solar system, then the odds are high that countless other travelers are already out there, passing silently, waiting for us to notice. In this way, the eccentricity of 3ix Atlas was not just a number, not just a record, it was a revelation, proof that the galaxy is alive with movement, chaos, and exchange, and that our solar system is but one small node in a vast cosmic network of wandering worlds. What makes 3I Atlas even more extraordinary is not only its extreme speed and eccentricity, but the fact that it appears to be dramatically larger than any other interstellar visitor we've ever recorded. When astronomers first began measuring its brightness, they calculated an absolute magnitude of around 11.9, which under certain assumptions could suggest a diameter of up to 24 kilometers if the object were a dark, inactive asteroid. Of course, as soon as the coma and faint tail were detected, it became clear that this was not an inert rock, but a living, breathing comet releasing gas and dust as it warmed in the sunlight. That means its nucleus is likely smaller than the initial maximum estimates, but even conservative calculations still suggest that Atlas is substantially larger than Oumuamua and Borisov, the only two confirmed interstellar visitors before it. To put that into perspective, Oumuamua was likely no more than a few hundred meters long, possibly shaped like a pancake or cigar, and Borisov's nucleus was thought to be somewhere between 400 and 500 meters. Compared to those, Atlas might be an order of magnitude larger, pushing into a size class that begins to rival some of the more substantial comets within our own solar system. This sudden leap in scale forces astronomers to rethink what kinds of objects actually get ejected into interstellar space. Smaller bodies are easier to accelerate out of a planetary system. They require less energy to escape their star's gravity. Larger ones, by contrast, need far more violent encounters to achieve the kinds of velocities necessary for interstellar travel. If Atlas really is as large as early estimates suggest, then whatever launched it on its million-year journey must have been a cataclysm of unusual intensity, perhaps a gravitational slingshot around multiple giant planets during a period of orbital instability, or even an explosive stellar event like a supernova shockwave. The sheer size also multiplies its scientific value. Larger comets preserve more material from different regions of their home systems, essentially acting as frozen archives of alien chemistry. A nucleus several kilometers across could contain layers upon layers of pristine ices and dust that date back to the formation of its parent star system billions of years ago. This makes Atlas a kind of time capsule from a world we may never directly see, its bulk protecting and preserving information that smaller, more fragile bodies might have lost during their travels. Of course, measuring size in astronomy is never simple, especially for an active comet. The coma, a glowing cloud of gas and dust surrounding the nucleus, inflates the object's apparent brightness, making the solid core seem much bigger than it actually is. Disentangling the contribution of the coma from the true reflection of the nucleus requires advanced observational techniques. Some scientists have suggested radar studies could penetrate the coma to bounce signals directly off the nucleus, though the comet's distance and rapid motion make this technically challenging. Others point to infrared data from the James Webb Space Telescope, which could detect the heat radiated by the solid core and help distinguish between reflected light from dust and thermal emissions from the nucleus itself. Until those measurements come in, size estimates will carry wide error bars, but already the numbers hint at something unprecedented. If confirmed, Atlas could represent an entirely new class of interstellar object, larger and potentially more complex than anything we've ever studied beyond our solar system. This realization comes at a perfect moment in astronomical history. The Rubin Observatory has only just begun operations, promising to transform our detection rates for interstellar visitors. The fact that one of the first it helped highlight could be a giant signals that the galaxy might be littered with such massive wanderers, many of them hidden just beyond the reach of our current instruments. Atlas's apparent size, then, is not just a matter of scale, it's a clue about population. It suggests that we may have been underestimating both the frequency and the diversity of interstellar comets, simply because smaller telescopes and older surveys were only catching the rare, bright ones that happened to come close. The discovery of a potentially massive visitor points toward a hidden population of interstellar giants passing silently through the dark. For astronomers, this opens thrilling possibilities: more material to analyze, more data to compare, and more chances to answer the fundamental question of whether planetary systems across the galaxy all follow similar patterns of formation and evolution. The size of Atlas therefore becomes a bridge between science and wonder. On one hand, it challenges models, demands better instruments, and pushes theoretical frameworks to account for violent ejection scenarios. On the other, it inspires awe by reminding us just how vast and unpredictable the galaxy is. Here is a frozen world, perhaps 10 times larger than the last, barreling through our solar system as casually as a leaf drifting on the wind, carrying within it a story written billions of years ago, in a star system far from our own. And though it will leave us soon enough, disappearing forever into the night, its size ensures that it will not leave quietly. Even from across millions of kilometers, its presence looms large in our understanding of the cosmos, rewriting what we thought we knew about the scale of interstellar messengers. The discovery of 3I Atlas did not just fall into the hands of professional astronomers armed with multi-million-dollar telescopes and advanced detection software. It became a shining example of how passionate citizen scientists can reshape the course of astronomical history. In fact, the story of this interstellar visitor cannot be told without acknowledging the role of ordinary people who devoted long nights and meticulous effort to combing through mountains of observational data. Sam Dean, an amateur researcher working from his home computer, became one of the central figures in the saga when he uncovered pre-discovery images of Atlas in archived telescope data that had gone unnoticed. His discovery pushed the observational timeline of the comet back by crucial days, providing astronomers with far more precise data to pin down its trajectory and prove its interstellar origin. Without that additional window of information, the calculations about its eccentricity and velocity would have remained rough estimates, instead of the hard evidence that confirmed Atlas as a true visitor from another star system. This episode demonstrates something remarkable. Astronomy has entered a new era where the boundary between amateur and professional is blurring. With the vast amount of data pouring in from sky surveys like Atlas, Pan-STARRS and the Zwicky Transient Facility, it is impossible for professional astronomers alone to examine every image in detail. Public archives make these datasets accessible, and anyone with patience, skill and curiosity can sift through them to make meaningful discoveries. The rise of citizen science is not just about providing extra eyes. It is about decentralizing discovery and allowing ordinary people to be part of unraveling cosmic mysteries. The case of 3I Atlas highlights how this democratization of science can change the game. Dean was not alone. After his breakthrough, other amateurs contributed to the unfolding story. Observers using remote telescopes in Chile and Spain confirmed follow-up images, while enthusiasts from across the globe coordinated online to share coordinates, brightness measurements, and potential trajectory refinements. In essence, a global community mobilized within hours of the official discovery, turning what could have been a narrow, localized investigation into a worldwide collaborative effort. This network of citizen scientists amplified the scientific output in ways that professional institutions alone could not have matched. Their contributions helped overcome one of the biggest challenges in tracking interstellar objects: the need for constant monitoring across multiple time zones and hemispheres. No single observatory can follow an object around the clock, but a distributed network of observers working from different parts of the world can fill those gaps, ensuring no crucial moments of data are lost. The success of this collaboration also underscores the power of modern tools. Remote telescope services allow amateurs to control professional-grade instruments from home, while online platforms make it possible to share raw data, analysis tools, and real-time updates instantly. What was once the domain of specialists locked away in institutions has become accessible to curious individuals willing to put in the work, and the benefits extend far beyond scientific results. This kind of citizen involvement brings public excitement into the heart of astronomy. When ordinary people realize that they can discover something as monumental as a visitor from another star system, astronomy becomes more than a distant academic pursuit. It becomes a shared adventure. Students, hobbyists, and even those with no formal training feel empowered to contribute, and this fuels enthusiasm for science in ways that no press release or textbook could replicate. In the case of Atlas, it was precisely this blend of professional rigor and amateur passion that made the discovery so robust and so widely celebrated. The lesson is clear: the cosmos is too vast, and the flood of data is too overwhelming for discovery to remain confined to a small circle of professionals. By opening the doors to citizen science, astronomy multiplies its reach and ensures that extraordinary objects like 3I Atlas will not slip through unnoticed. The comet, in this way, does not only teach us about alien worlds, it teaches us about the potential of humanity when curiosity and collaboration are allowed to flourish. For every professional telescope aimed at the stars, there are countless amateurs ready to scan, measure, and analyze, all united by the same hunger to know what lies beyond. The story of 3I Atlas is as much about them as it is about the object itself. A testament to how discovery in the modern age has become a truly global and collective endeavor. 3I Atlas almost became the interstellar visitor that slipped past humanity's gaze, hiding in plain sight against one of the most challenging backgrounds in the night sky, the galactic center. This region, located in the constellation Sagittarius, is crowded with billions of stars, dense star clusters, and veils of interstellar dust, creating a chaotic visual field that makes detecting moving objects incredibly difficult. When the comet first entered our solar system, its faint light was nearly lost in this overwhelming backdrop, camouflaged like a grain of sand on a crowded beach. Automated detection systems designed to spot subtle motions against relatively sparse star fields struggled to distinguish its faint movement from the brilliance of countless stars. Imagine trying to notice a single snowflake falling during a blizzard, and you get a sense of the monumental challenge astronomers faced. For several weeks, Atlas drifted silently through this stellar chaos, evading detection despite the sophisticated surveys scanning the sky every night. It was not until it emerged from the densest part of the galactic bulge that algorithms began to flag it as unusual. By then, crucial observation time had already been lost, though thankfully enough remained for astronomers to piece together its trajectory and identity. This near miss revealed something profound. Even with today's advanced detection technology, there are blind spots in our observational strategies. The galactic center is one of them. Its crowded environment, combined with the scattering and absorption effects of interstellar dust, creates a natural camouflage that can hide objects, even those with extraordinary speeds and trajectory. The case of Atlas forces astronomers to rethink how to monitor these regions more effectively, since they may conceal not only harmless cosmic wanderers, but also potentially hazardous objects whose paths could cross dangerously close to Earth. Adding to the difficulty are the complex phenomena of gravitational lensing and light distortion caused by massive objects in this part of the sky. These effects can shift the apparent positions of background stars, creating illusions that confuse automated detection systems further. For Atlas, this cosmic camouflage almost worked perfectly, keeping it invisible until it shifted just enough for its unusual motion to stand out. But what makes this story remarkable is how human persistence broke through the camouflage. Sam Dean, the citizen scientist who trawled through archival data, managed to uncover pre-discovery images dating back to mid-June, showing that Atlas had been right there all along, hidden within the noise. His ability to spot the breadcrumb trail in such a cluttered environment underscores the irreplaceable role of human intuition, even in an age of algorithm. The irony is striking. Atlas likely originated from the galactic disk and carried instrument about environments near the galactic center, one of the most scientifically valuable regions for understanding star formation and planetary system evolution. Yet, the very richness of that region almost prevented us from noticing its arrival. The galactic center teaches astronomers both a lesson in humility and a challenge to innovate. As the universe sends us these messengers, they may come from the most difficult regions to watch, and if we are not vigilant, their secrets will slip by unnoticed. 3I Atlas reminds us that detection is as much about persistence and creativity as it is about technology. It slipped past our systems for weeks, but thanks to global collaboration and the determination of both professionals and amateurs, its story did not remain hidden. Instead, what was nearly the greatest interstellar object that got away became a symbol of how discovery often hinges on looking harder where the odds seem stacked against us. When astronomers finally confirmed that 3I Atlas was not only an interstellar object, but also an active comet, the scientific community felt both relief and excitement, because unlike Oumuamua in 2017, which left more questions than answers, this visitor appeared to behave exactly as a comet should. Early data revealed a faint but unmistakable coma, a hazy cloud of gas and dust surrounding the nucleus, along with a short tail measuring only a few arc-seconds across the sky. This activity was conclusive proof that the object was not a dry asteroid, but a true comet, steadily releasing material as solar heating began to affect its icy body after millions of years, drifting in the freezing vacuum of interstellar space. Observations from the Nordic Optical Telescope, led by respected astronomers David Jewett and Jane Liu, gave the final stamp of confirmation. Their detailed measurements showed that the comet was clearly active, venting gas and dust into space, exactly as theory predicted. For scientists who had wrestled with Oumuamua's bizarre lack of activity and strange trajectory, this was a refreshing change. 3I Atlas was behaving normally, allowing researchers to apply familiar comet science to an extraordinary object. This reliability made Atlas particularly valuable. It meant that rather than puzzling over exotic explanations, astronomers could use established tools and models to probe its chemistry, structure, and behavior with confidence, while still gaining insights from the fact that it originated in another star system entirely. Even in its ordinariness, however, 3I Atlas was extraordinary. It marked the first time in history that humanity could study an interstellar comet from the very moment it woke up, after eons in the deep freeze. For millions of years, its surface and interior had been preserved at near absolute zero, untouched and unaltered, except for the faint bombardment of cosmic rays. As it approached the sun, solar radiation began sublimating the ancient ices, turning them directly into gas and creating a thin, glowing atmosphere. This transformation offered a priceless opportunity. The gases and dust released during this first exposure contained pristine material from the object's birth system, preserved like a time capsule from billions of years ago. By studying its coma and tail, astronomers could essentially read the chemical fingerprints of another planetary system without ever leaving our own. Telescopes quickly detected that the coma was reddish in color, much like that of Borisov, the interstellar comet, discovered in 2019. This reddish glow suggested the presence of complex organic compounds and fine dust particles, substances thought to be widespread in the outer regions of planetary systems. Such consistency between Borisov and Atlas hinted strongly at universal processes in planet formation, implying that icy comets in many star systems share the same basic chemistry. If true, this would mean the building blocks for planets, and potentially for life itself, are not rare but common throughout the galaxy. The composition of the gases released gave even deeper clues. Spectroscopic studies began identifying water vapor, carbon monoxide, methane, and other volatile molecules, each with unique spectral fingerprints that told a story about the conditions where the comet had formed. Larger dust grains escaping from its surface indicated fresh material being revealed, while smaller particles hinted at ancient processing during its long journey through interstellar space. Despite its promising behavior, astronomers faced a sobering challenge: time. 3I Atlas would only remain observable for a narrow window before solar glare overwhelmed it. By October, it would pass close to the sun, making ground-based observations nearly impossible until it re-emerged months later, fainter and less active. This urgency sparked a global campaign unlike any before, with professional observatories and amateur astronomers coordinating night after night to extract as much data as possible before the opportunity slipped away. From Chile's Atacama Desert to Hawaii's Mauna Kea, from Europe to Australia, telescopes of every size turned toward the visitor. The James Webb Space Telescope, with its unparalleled infrared sensitivity, was tasked with probing its thermal emissions and chemical composition. These observations were critical because infrared wavelengths can reveal heat signatures and detect molecules invisible in visible light. At the same time, the European Southern Observatory's Very Large Telescope carried out spectroscopic studies to pin down exactly what elements and compounds were streaming off its surface. For all its scientific value, Atlas was never going to be a spectacle in the night sky for casual observers. At magnitude 18 by 8, when first spotted, it was far too faint to be seen with the naked eye or even backyard telescopes. Only the most advanced equipment could capture its image, and only with patient observation. Yet what it lacked in brightness, it made up for in significance. Every photon of light it released carried information from a world beyond our solar system, and every observation brought humanity one step closer to understanding the universality of cosmic chemistry. In its faint coma and short tail lay secrets about the birth of worlds, the building blocks of planets, and perhaps even the seeds of life. 3I Atlas might not have dazzled the casual stargazer, but for the scientists racing to record its fleeting presence, it was a cosmic treasure, proof that the galaxy is alive with wandering messengers, each one waiting to reveal a piece of the greater story of creation. As 3I Atlas continued to blaze its path through the inner solar system, astronomers turned their attention to the crucial matter of size. Unlike Oumuamua, whose peculiar elongated form left researchers uncertain about its exact dimensions, or Borisov, which was small enough to be quickly catalogued as an interstellar comet, 3I Atlas appeared to be in an entirely different league. Early brightness measurements suggested an absolute magnitude around 11.9, which, if it were a dark, inactive body, could correspond to a staggering diameter of nearly 24 kilometers. Of course, brightness alone does not equal size, since much of the light came from the coma and dust clouds surrounding it. But even after adjusting for this effect, the nucleus of 3I Atlas appeared to be far larger than either of its predecessors. Oumuamua was only a few hundred meters across, and Borisov measured about 400 to 500 meters. In contrast, Atlas seemed to stretch into the tens of kilometers, a colossal scale that suggested it was a different class of interstellar wanderer entirely. The implications of such size were profound. For an object of this magnitude to be hurled out of its birth system and given enough velocity to cross interstellar space, the violent processes involved must have been extraordinary. Smaller comets can be ejected during planetary migrations or close gravitational encounters, but to fling something as massive as Atlas would have required enormous energy. One possibility is that it was expelled during the early chaotic days of its home system, when giant planets shifted orbits and destabilized surrounding debris. Another scenario suggests an even more cataclysmic event, perhaps a stellar encounter that sent shockwaves through the system's outskirts, or the collapse of a nearby massive star whose explosion imparted tremendous gravitational kicks to neighboring bodies. Regardless of the mechanism, its sheer size spoke of extreme astrophysical processes, hinting at a dramatic past in a distant star system millions of years ago. The size also made Atlas a goldmine for science. Larger comets preserve more complex histories within their cores. Their vast reserves of ice, dust, and organic material can contain records from multiple regions of their original planetary system. If Borisov and Oumuamua gave us glimpses of individual chapters of alien formation, then Atlas promised an entire library. Its nucleus could shelter volatile compounds frozen since the system's infancy, offering direct samples of chemistry that occurred billions of years ago around a distant sun. Because comets form in the outer reaches of planetary systems, where ices condense and accrete, their compositions preserve the fingerprints of those environments. By studying Atlas's gases and dust, astronomers hoped to decode the unique DNA of its home star system and compare it with our own Kuiper belt and Oort cloud bodies. Yet pinning down the true size was not simple. The coma surrounding Atlas reflected sunlight, making the nucleus look brighter than it really was. This uncertainty meant the nucleus could be somewhat smaller than first estimates, but even conservative calculations placed it far above its predecessors in scale. To address this challenge, astronomers turned to advanced methods. Radar observations, though difficult at such distances, were considered as a way to pierce through the coma and bounce signals off the solid core. The James Webb Space Telescope, with its infrared sensitivity, offered another approach, detecting the nucleus's thermal emissions separately from the surrounding dust. By analyzing these emissions, researchers could better estimate its true size and surface properties. The possibility of a giant interstellar comet had wider implications too. If objects of this magnitude could travel between star systems, then the population of interstellar wanderers might be far more diverse than previously thought. Some could be rocky asteroids, others icy comets, and now perhaps even large, complex bodies rivaling the scale of Earth's own great comets. A larger size also increased the likelihood that such objects could transport significant amounts of organic compounds or even prebiotic materials across star systems. This fed into theories of panspermia, the idea that life's ingredients might spread through the galaxy via comets and asteroids. While 3I Atlas posed no threat to Earth, its mass and speed reminded scientists that interstellar visitors are not always small curiosities. Some are titans carrying the raw materials of worlds. The global campaign to measure its size was as much about preparation for the future as it was about understanding this single object. Each new interstellar visitor helps refine detection methods, shape observational strategies, and test instruments. With the Rubin Observatory in Chile now fully operational, astronomers expect discoveries of interstellar objects to multiply dramatically in the coming years. Understanding Atlas's true scale would help calibrate those future detections, offering benchmarks against which to measure the diversity of incoming wanderers. Ultimately, Atlas's enormous size served as both a scientific gift and a cosmic warning. It confirmed that planetary systems are capable of ejecting not only small fragments, but also massive bodies into the galaxy. It demonstrated that these objects can cross interstellar space intact, surviving radiation, cold, and collisions long enough to enter another star system. For astronomers, it was an unprecedented opportunity to study alien materials up close, preserved within a nucleus large enough to hold secrets untouched for billions of years. For humanity, it was a reminder of the immensity of the galaxy and the incredible forces at play in shaping worlds both near and far. 3I Atlas was not just another interstellar object. It was a giant, a messenger of cosmic proportions, carrying with it a silent story of creation, destruction, and survival across the stars. As the story of 3I Atlas reached its most critical phase, astronomers around the world were forced to confront the limits of time. Interstellar visitors are, by their very nature, fleeting. They arrive unannounced, pass quickly through the inner solar system, and then vanish forever into the darkness, leaving only the data captured during their brief stay. Section 10 of this unfolding saga is about urgency, the narrow window in which humanity must act to learn as much as possible before the opportunity slips away. For 3I Atlas, that window is already closing. Its trajectory ensures that it will pass close enough to the Sun in late October to spark dramatic activity, but also close enough that solar glare will obscure it from most ground-based telescopes for several months. By the time it re-emerges from behind the Sun in December, it will be fainter, less active, and speeding irreversibly outward. This ticking clock has set off a global race among observatories, each vying to capture as much data as possible before the comet disappears into interstellar space forever. The challenges are immense. From Earth's surface, telescopes can only track Atlas during nighttime hours, and only when it is far enough from the horizon and away from the sun's glare. Each passing night shortens the available observing time, and in the northern hemisphere, astronomers have already lost sight as its position drifts southward. Southern hemisphere observatories have picked up the task, but even there, the comet's trajectory and the seasonal shifts limit opportunities. For many astronomers, the realization is sobering. The next few months may be the only time in human history anyone will see this object. And unlike planets, moons, or long-period comets, it will never return. This urgency has brought out the very best of global cooperation. Agencies such as NASA and the European Space Agency have coordinated with university teams, amateur astronomers, and citizen scientists to create a comprehensive observation plan. The James Webb Space Telescope, positioned at the stable L2 point, offers a rare advantage. Its infrared instruments can analyze thermal emissions and chemical signatures invisible to optical telescopes, and its location allows it to continue observations even as Earth-based facilities struggle against the sun's interference. Webb spectrographs are already scanning the coma for signs of water vapor, carbon compounds, and organic molecules, while its thermal imaging instruments are mapping the heat distribution across the dust cloud and nucleus. Meanwhile, the European Southern Observatory's Very Large Telescope in Chile and the Lowell Discovery Telescope in Arizona are tracking brightness variations, measuring light curves that could reveal the object's rotation period, shape, and surface irregularities. Amateurs equipped with advanced imaging systems are contributing vital data as well, filling in gaps between professional observations and helping track subtle changes in the coma and tail. This unprecedented collaboration reflects how astronomy has evolved in the 21st century, no longer the domain of a few elite observatories, but a distributed network of eyes and instruments working together across the globe. Yet even with this massive effort, limitations remain. The comet is faint, nearly 2.5 million times dimmer than the North Star. Capturing detailed spectroscopic data requires long exposures and precise tracking, a difficult task given its rapid motion across the sky. Every night lost to bad weather, equipment malfunctions, or scheduling conflicts means irreplaceable data slipping away. Astronomers are prioritizing their measurements carefully, focusing on those most likely to reveal insights into its chemical makeup, thermal properties, and origin. The hope is that even with limited time, they can build a dataset robust enough to stand for generations, providing clues long after the comet itself has faded from view. The urgency is not only scientific but also philosophical. For many researchers, 3I Atlas represents more than just a rare interstellar comet. It is a messenger from another world, carrying with it the chemical record of a planetary system we may never otherwise study. Every molecule of gas it releases, every dust grain it sheds, is a direct sample of alien chemistry, a fragment of a cosmic history, billions of years old. To miss the chance to study it in detail would not just be a scientific loss, but a human one. It is a reminder that we live in a universe filled with wonders, but that our opportunities to touch them are often fleeting. In many ways, the urgency surrounding Atlas foreshadows the future of interstellar object science. With the Rubin Observatory now operational and expected to detect many more such visitors in the coming decade, astronomers are refining their strategies. They know that each visitor brings only a brief chance to study the raw materials of distant star systems. If we are to unlock their secrets, we must be ready from the moment they appear, with instruments calibrated, teams coordinated, and observation plans in place. Atlas is teaching us not only about itself, but about how to prepare for the cosmic guests yet to come. Section 10 closes with a sense of both tension and awe. The countdown has begun. The final weeks of close observation are underway, and astronomers around the world are straining every resource to seize the moment. The comet will soon be gone, racing back into the void from which it came, but the data captured in this brief window will endure, shaping our understanding of planetary formation, interstellar chemistry, and cosmic history. 3I Atlas reminds us that science is often a race against time, and that in the fleeting passage of a celestial visitor, humanity must act quickly, boldly, and collectively to grasp the secrets written in the stars. The conclusion to the story of 3I Atlas is not just an ending, but a reflection on what it means for humanity to witness and study such a rare visitor from beyond our solar system. When astronomers first spotted this interstellar object in July 2025, It represented more than just another celestial body passing through the night sky. It was a tangible connection to distant worlds, a cosmic traveler that had wandered through the galaxy for millions of years before finally crossing paths with Earth. Now, as its brief stay comes to an end, the urgency and excitement surrounding its discovery give way to deeper questions about our place in the universe, the mysteries that remain hidden in interstellar space, and the opportunities that future discoveries may bring. 3I Atlas has reminded us how fragile and fleeting such encounters are, and how much they reveal when studied with focus, cooperation, and innovation. From the very beginning, the object defied expectations. Its velocity alone, more than 66 kilometers per second relative to the Sun, placed it firmly outside the bounds of our solar system's gravitational hold. Unlike asteroids or comets native to our neighborhood, it followed a hyperbolic trajectory, ensuring it would enter once and never return. Its orbital eccentricity of over 6 represented the most extreme ever recorded, and its sheer speed hinted at violent origins, a possible gravitational slingshot from giant planets in its home system, a close stellar encounter, or even the aftermath of a supernova. This was not just another rock drifting through space. It was the survivor of cataclysmic events, carrying with it the chemical and physical imprints of its birthplace. The chance to study such a messenger was extraordinary, and scientists knew they had only months before it would vanish forever. The comet's activity added to the fascination. Unlike Oumuamua in 2017, which puzzled astronomers with its strange shape and unexplained acceleration, or Borisov in 2019, which appeared more like a typical comet, 3I Atlas offered the perfect balance of familiarity and novelty. It behaved like a comet should, developing a coma and a tail as solar radiation heated its icy surface. Yet it was significantly larger and faster than its predecessors. Spectroscopic studies revealed water vapor, carbon monoxide, methane, and complex organic compounds, providing direct evidence of chemistry that mirrored what we see in our own solar system. These findings reinforced the idea that the building blocks of planets and potentially life are not unique to Earth or even to our Sun, but widespread across the galaxy. Atlas confirmed what many had long suspected, that planetary systems form through universal processes, governed by the same physical laws everywhere, producing comets and asteroids rich in volatile materials that can travel between stars. Equally significant was how the discovery unfolded. Professional astronomers may have sounded the alarm, but it was citizen scientists like Sam Dean who scoured archived data and uncovered pre-discovery images that extended the timeline of observations. Amateurs using remote telescopes and shared databases played crucial roles in refining its orbit, confirming its interstellar origin, and providing additional measurements of brightness and activity. This collaboration between professionals and amateurs showed how modern astronomy is no longer confined to a few elite institutions. Instead, it is a global effort, open to anyone with curiosity, persistence, and access to the right tools. 3I Atlas may be remembered as much for the way it united the astronomical community as for the scientific data it yielded. As it leaves the inner solar system, bound for the infinite dark, 3I Atlas carries with it the secrets of its birth system, secrets humanity will never fully know. Yet in the short time it was with us, it offered glimpses of those secrets through the dust and gas it shed, the spectra it revealed, and the trajectory it traced across the heavens. Its passage was fleeting, but its impact will last for decades, shaping the science of interstellar objects and inspiring the next generation of astronomers who will stand ready for the cosmic messengers yet to come. The conclusion is simple but profound. 3I Atlas was not just a comet. It was a reminder of our connection to the broader galaxy, a symbol of the mysteries waiting in the void, and proof that even in the vast emptiness of space, We are not alone in our cosmic journey.